We are going to learn indexing and multiway trees, which belongs to Unit 5. So, what is indexing? So, when you want to retrieve data from a database, it is always easy if your files are stored in such a way that it can be indexed. You can call it using an index pair, that the pair is of form, key value and address. Suppose I want to retrieve student data. So suppose the index is 100, I'll give the key value and address pair in that format, and I will retrieve the data of a roll number 100. So indexing is an effective way of retrieving records from the database. Now there are different types of indexing. You have cylinder surface indexing, hashed indexing and tree indexing. Cylinder surface indexing is similar to the hard disk of your system, wherein the hard disk is divided into different cylinders, surfaces and blocks. So if you want to retrieve a data, you will give the cylinder number and the surface number, and then you can retrieve that particular record in that cylinder and surface. Hash indexing, we have studied in Unit 1 how data is stored in a hash table using where data is stored using a hash function and retrieved also with the help of a hash function. So you know that. Then the next is tree indexing, where you place our records in a tree data structure. So, what is a multi-way search tree? So, M-way search tree or multi-way search tree is a generalized versions of binary search trees where each node contains multiple elements. So, in the previous examples or in the tree, when we learned about a single node having at most two children. So, here you can have a node which can contain multiple values and multiple children. So, that is why it's called a multi-way search tree. So as you can see in the example, you can see a node which contains 3 values and it contains 4 children. So that is why it's called a multi-way search tree. So an M-way search tree is an of order M, contains a maximum of M minus 1 elements and M children. So that is the property, and the goal of an M-way tree is of height h calls for big O of h number of accesses for insert, delete and retrieval operations. So this is the now all about multi-way search tree. Next, before we start with the operations performed on a binary B tree, we have to know the certain properties of a B tree. So a B tree is a self-balanced tree in which every node contains multiple keys and has more than 2 children. As I've already told in the previous slide, a B tree of order M has the following properties. That is, all leaf nodes must be at the same level. That means the last level, all the leaf node will be at the same level. Then all nodes except the root must have at least m divided by 2 minus 1 keys and maximum of m minus 1 keys. The property 3 states that the non-leaf nodes except the root must have at least m divided by 2 children and at most m or m children. That means a maximum of m children is allowed. For 4 property, the root has at least 2 children and contains a minimum of 1 key. 5 says a non-leaf node with n minus 1 keys must have n number of children. All key values in a node must be in a ascending order. So these are the properties that has to be followed when any kind of operation is done on a B tree. The next, you can see this is an example B tree of order 4. So order 4 means it can have m divided by 2. So you can have children. This is allowed. So m divided by 2 minus 1. That means the at least 1 key should be there and maximum of m minus 1. 3 keys. That is why 3 places have been given for a particular node, and all leaf nodes, as you can see, is at the same level, and all non-leaf nodes except the root must have m divided by 2, that is 4 divided by 2 children at least. So you can see at least, so here there are 3, at least 2 children should be there. And if the root node is a non-leaf node, then the root node must have at least 2 children. A non-leaf node with n minus key must have n number of children. So that is all the rules that has to be followed in a B tree of order 4. So the operations on a B tree, so as we have seen before, first read the search element from the user, and you compare the search element with the first key value of the root node in the tree, and if both are matched, then you display the given node is found and terminate. If not, you check the and search whether the element is smaller or larger than the key. If it is smaller, then continue to the left subtree. If it is larger, you compare it with the next key value, and the same process 3, 4, 5 and 6 will be done until the search element compared is the last key value of the leaf node, and if it is the last key value, then you will display the message that the element is not found. So we'll understand this using an example. So you can see here, if you want to search element 17, so first you search with 11. As you can see here, you search with 11, and then since 17 is greater than 11, you go to the right side, and then you search with 16. Now you see 17 is greater than 16, so you search with the next key value. So the next key value is 18, so that means it will be in 17 might be in the left child of 18, that is the value is going to be between 16 and 18. So when it's checked with the 18's left child, you find 17 over there. So that's how you get the value 17 if it is there. Now it's of degree 3. Why? So you can see at most 2 key values are there, and at most 3 children can be found. So here you can see how the process is done. Next, the operations, insertion operation. You have to check whether the key is empty, tree is empty. If the tree is empty, then create a new node and the new key value and insert it into the tree as a root node. If it is not empty, you find a suitable leaf node to which the new key value is added using the binary search tree logic. And if the tree leaf node has an empty position, you add the new key to the empty position. And if it is already full, you split the leaf node by sending the middle value to the parent node and repeat it until the sending value is fixed into a node. So this splitting is performed at the root node, then the middle value becomes a new root node for the tree, and the height of the tree is increased by 1. So we can see an example here. See, first time inserting 1, so it is the tree is empty, so you can directly insert, and it's of order 3. That means at most 2 values can be there. So I've put a node with 2 values, and 1 value is inserted with as 1. Then I insert 2, since 2 is greater than 1, and there is a vacancy in the right side of that node, you place 2 over there. Then when I insert 3, you can see the node is full. So I split the node by moving the middle element to the top, and 2 becomes the root element. Similarly, 4, you can see that 3, it is greater than 3, and the right side of the 3 had a vacant space. You place 4 over there. For inserting 5, you can see 5 is greater than 2, 5 is greater than 3, 4. So 5 will be placed here, but the node is full. So you split the node in the middle and you move 4 on top. And since there is a space over there, you place 4 next to 2. Then I want to place 6. As you all can see, the same process is continued for placing 6, 7. As you can see in the example 8, 9 and 10. So this is how a B tree insertion is done. I hope you understood this.